Welcome to STMU-SET Spotlight, where we explore the stories and people shaping the future of science, technology, and education. I'm your host, Dr. Paul Uhlig, Chair and Professor of Mathematics. Today, I'm thrilled to welcome two new colleagues who recently joined our faculty in the Department of Chemistry, Biochemistry, and Physics. They both bring exciting research programs, deep commitments to teaching, and a passion for mentoring future scientists. Let's welcome Dr. Patrick Oladamehin and Dr. Emily Lancaster.
Hello.
Thank you.
Let's start with a question for both of you. You both recently joined St. Mary's. What has the transition been like so far, and what drew you here?
Go ahead.
It's been great for me. Coming to St. Mary's from day one, I was able to feel at home because everyone was very welcoming, and it was just easy for me to adapt to the environment that St. Mary provides, the family culture and all of that. Then with regards to the school in particular, I was in academics for a long time and decided, should I try industry? So I left. I went to industry for a while and decided I wanted to come back to academia. So I applied to different schools, went for different interviews. But before I made my decision, I had to look at the mission of each of the school. And part of what drew me to St. Mary's is actually the mission of St. Mary University. St. Mary is a school where we're not just interested in educating the person, we're also interested in who the person is becoming in the process, right? We're educating you for service, for justice, for peace, so it's like educating the whole person. That really aligns with my core values and what's, I like, and it was an easy decision for me to make.
Wow.
Honestly, Patrick, you really set me up well because you set up the mission and how it aligns so well with you personally, and I can't agree more. The attitude here at St. Mary's is so welcoming. It's a small environment, which I've always really liked. I feel like I could approach anybody, faculty, staff, or undergraduate student, ask help, and people would be willing to give it with no judgment too, right? And it's one of the nice day-to-day feelings that I have here. But my transition to here, I've been working over a decade to get to this exact position. This is literally my dream job. At a minority-serving institution, primarily undergraduate, doing research and advancing the coursework, teaching at an advanced level. This is literally what I've been working for, and I'm so pleased to get it. Transition from postdoc, where I was, to primarily teaching has been really weird, though. It's such a different mentality where you're doing research at an R1 institution where the focus is you are in lab, you are getting data, that is your job, you monkey, right? like please just get the data. And coming here, it's such a flipped script. It is the classroom, it is the mentorship in the office hours, and although I do spend a lot of time in lab, it's just not the same core focus. And I don't mind it at all. It's just everything complementary. And this is just where I love to be.
That's really wonderful. The university does a great job of integrating scholarship, teaching, service, and really highlights the importance of the interpersonal, those relationships that we have as colleagues and with our students. It's really been huge for me being here for over 29 years. Patrick, your work dives into computational chemistry, looking at molecular dynamics and quantum modeling for drug discovery. Can you give us an overview of the kind of problems you're trying to solve and how techniques like density functional theory, DFT, play a role?
Yeah, certainly. So looking at it from a big picture perspective, my research is focused on molecular recognition, how these molecules find each other, how they interact with each other, and how these interactions actually affect the biological function of the system. So I use molecular dynamic simulation and quantum mechanical methods as complementary tools So for molecular dynamics simulation, is like we're analyzing the physical movement of atoms, molecules over time. So with that, we're able to predict how the system is going to behave, probably how it would misbehave. Just we're able to answer questions from looking at the system as a whole. With molecular dynamics simulations, we can, simulate systems with thousands of atoms, millions of atoms. So it's easy for us to work with these big systems and ask questions about how they bind, how they change conformation, and all of that. Is really based on classical Newtonian mechanics. So for molecular dynamics, we just look at the atom as point charges, basically. Why quantum mechanics is different in a way, because in quantum mechanics, now we're zooming in. We're not just looking at the atom as point charge. Now we're treating the electrons explicitly. Now we're looking at the atom as something that has a particle that has nucleus surrounded by electrons. So we're thinking about how the electrons are distributed and how would this electron distribution affect the shape of a molecule, affect how the molecules are going to interact. So I use both tools in a complementary way. My main research focus is in antibiotics cell wall interaction. So I'm asking the question, how can we stop bacterial resistance basically to antibiotics? And the antibiotics, they target different parts of the bacterial cell. They can target the RNA mechanism, the DNA, all of that. But my focus is on antibiotics that target the bacterial cell wall. And these antibiotics, as at 2020, they are actually about 50% of antibiotics in the market. So I target these antibiotics. I like to see my research in a way. An analogy I use is I'm trying to break down the bacterial cell wall. When the bacterial cell wall is intact, then it's easy for the bacteria to withstand any antibiotics attack, right? So I'm asking the question, what changes? Because the bacterial cell wall in itself is dynamic. It's not like the bacteria has a particular cell composition that it's always going to have. It's really dynamic. In fact, with bacterial cell, the question is not if it would be resistant to a particular antibiotics, it's when. It's when is it going to be resistant to particular antibiotics. So we're studying how it's coming up with this resistant mechanism. Sometimes it's surprising. Sometimes it can just be one atom change that will reduce the potency of a particular antibiotic. So just studying these interactions and thinking about what kind of changes can we make, understanding the forces of interaction at fundamental molecular level, in order to be able to make better prediction. So just look at it as you're trying to understand how to ride a bike. So you need to look at how the wheels are connected, the gears. You need to look at it at, a microscopic level for you to be able to make changes that would affect the bike as a whole.
And you're doing all of this in computer simulations of the molecules and the cell walls and the like.
Yeah, that's the beauty of it. We don't get ourselves wet. Everything is in computer. Though I've done a bit of wet lab. I worked in a biosafety tool lab before. The kind of research I'm doing on computers, I've actually done it in the lab, in wet lab, where I use, mass spec and all of that to understand how the bacterial cell is changing, regulating its cell wall component based on the challenging environment that it finds itself, So it's like a full cycle. I've seen it in experiment. Now I'm trying to do the simulation aspect of it. But the beauty of simulation, computational chemistry to drug discovery is that when we do this simulation, it reduces time wastage. The time you're going to use to synthesize a particular molecule in the lab, then try to see if it's going to work, if it's going to do what you want it to do, that time is minimized because now we can predict it using computer simulations and tell you what molecule you should try to synthesize.
That's amazing. Emily, your background is rooted in enzymology and medicinal chemistry. from characterizing unusual enzymes to postdoc work on pediatric cancer pathways. Can you share how your research journey evolved and what kinds of questions you're exploring with your students here at St. Mary's?
Yeah. So when I knew that I wanted to go into teaching in late undergrad, I knew that I wanted to get the Ph.D. and I wanted to be at the lead of a classroom. I initially thought I was going to get a Ph.D. in organic synthesis. And I went to my Ph.D. program and I started doing work in organic synthesis. And I quickly realized I am not good at this. And I quickly changed gears to enzymes, where it's a nice middle ground between the synthesis, making molecules, and protein work, where these enzymes are evolutionarily, evolved to get to make this particular step of this particular chemical. And what drew me to academia and being in front of the classroom was actually also antibiotic research and trying to make new drugs synthetically. And then when I switched gears into enzyme focus, it was how can I get enzymes to do the chemistry for me? And how can I figure out how enzymes work to make the chemistry, make the drugs, but also figure out, is this an enzyme in, say, a bacterial pathway that we can target to make new drugs? And then that was my graduate focus, where enzymes are very well structured. They have a very predictable fold, usually. And the way enzymes work is that the sequence is very unique to that enzyme. The sequence then dictates how the structure will look. And then based on how that enzyme looks, it will function a certain way. And we call that the structure-function relationship. And that was hammered into me during grad school. And then I went to my postdoc at UT Health in San Antonio. And I joined a lab where the focus was essentially wet spaghetti for proteins. No structure. They're still proteins. They're not enzymes, but they're proteins that have no appreciable structure for any length of time. And they are everywhere in the body, which is fine. That's not inherently a bad thing, but it's kind of the Wild West of protein rules. And for so long, I think the community has been avoiding studying these disordered proteins because we were like, please don't be important to health. We don't know how to study you yet. And turns out, of course, it's important. And so currently our technology is not advanced enough to properly study these things to where we can see what these disordered proteins look like. And unfortunately, because there's not as advanced technology and we're a little behind in studying disordered proteins, they're currently, I guess you could call it, winning the cancer war, where some cancers are started from this connection to disordered proteins, wiggly proteins that are involved somehow. We're not sure how they're involved, but we know that some disordered proteins can cause the pediatric bone cancer Ewing sarcoma. And if it's mutated in such a way that it partners with this other half of an enzyme, then you have an 85% chance of developing Ewing sarcoma as a child. And those statistics are, you can't ignore those. So obviously we're going to go into it, but again, it's just hard. We have these classic techniques, crystallography. NMR is currently the most powerful tool to get an idea of what these things look like. But these computational methods that Patrick is working on are going to be very effective in crossing that bridge before technology advances to where we can actually see the minimal structure that these disordered proteins have. At least Patrick, with his in silico modeling, can give us closer to predicting, well, at this certain point, this string of atoms can look this way. Now let's start to figure out, if it looks this way, how does it behave? And so, we'll talk about this later, but I'm really excited about what Patrick brings to the university for his research, kind of selfishly, because I'm like, oh, yeah, I'm going to definitely lean on you for advancing my work as well. But what was the question? Let's see. Oh, yeah, that's right. So I started in organic synthesis, realized I don't like it. And that's not true. I like it. I'm not good at it. Just don't have the hands for it. Switched to enzymology. And so I think my my journey, I guess, could be described as, or the theme would just be protein work in general, but going from really structured proteins to the wet spaghetti noodles, the Wild West, and getting that full spectrum of how proteins work enzymatically or non-enzymatically in relation to human health. And I care about all of those things. And I'm still interested in antibiotic research, even though I'm not focused on it right now. I definitely care about making new antibiotics, but we have to study the targets to figure out what we're going to synthesize first. So
as you describe all that, my mind goes to the nearest mathematical topic that it can associate with such thing, and that's combinatorics. It's just looking at all the ways these molecules can combine.
yes, and there's only so many.
Yeah, and yet there's many.
Yes,
and that's a big part of the problem and the context in which they're combining.
and the splendor of it. Like there's only so many, but so many combos, and you're like, I don't know, in awe, but also, I don't know, sometimes overwhelmed. I don't know. You get overwhelmed?
Yeah.
Thank you. Okay. I'm glad I'm not the only one.
Well, I know who might get overwhelmed, and that's your students. So how do the two of you get students involved in your research, Emily?
So for me, I think it starts because I am a loud, bubbly person, and part of my teaching philosophy is to break down the stigma or that wall that some students have that science and research isn't accessible to them because they may feel like they lack confidence or capability. And one of my goals is to make them aware, like, no, like you're fine. Like maybe not right now, you're the scientist that you picture yourself, but we'll get you there. We'll get you started. And all it takes is just one conversation. Just talk to a faculty member, see what's available for you, see what you like, and we'll try to get you in lab. And really, by that point, they're hooked, I think.
Yeah, certainly. And also as a department, we have a particular class that does seminar for freshman students especially. And faculties come and give presentation. We come to tell them about the kind of research we do, try to dilute it in a way that they can really, understand. So for me, it's just, whenever I think about getting students into my research, it's just how can I trigger their curiosity, right? How can I excite them with the kind of problems you're trying to solve and the kind of tools that they're going to be armed with, So I try to let students know that, yes, you're here, you need to pass your classes, but you should look beyond your classes, right? Because after all the classes graduation, you're going to be in the outside world, and in the outside world, probably everyone took that particular class. So what makes you different? What kind of exposure did you have? So having a research experience armed with some of these tools, for example, in my research, I teach them basics of coding, Python, programming, and different stuff, molecular visualization and all of that. And these are things that they can put on their resume. So that easily gets them excited. And another thing is, as faculties, sometimes we apply for grants, as individually and also as a department, so we do pay students to actually do research, right? So in the summer, I paid a particular student lots of money to do research, was able to take care of her accommodation and all of that. So it's just all exciting, Yeah.
Yeah, at St. Mary's, there's such an emphasis for getting students involved in research, which is so neat because you're building into these courses, a lot of the times, these novel research questions and projects. And like you're saying, we, as part of just learning the course, doing the class, getting the grade, you're getting these skills that I'm like, put those on a CV. Like it makes you a way more enviable candidate when it comes to progressing your career and applying for jobs. And it's also the environment because there's research opportunities everywhere. It's commonplace to be like, oh, are you doing research with so-and-so? And students will be like, oh, no, I'm going to actually do research with so-and-so instead this year. And it's like, oh, it's just a commonplace kind of language.
Yeah.
An essential feature of all of this is the excitement and love of what you do that is infectious with the students that gets them involved.
Certainly.
The institutional emphasis on undergraduate research is great, but without your, and I would say truly infectious excitement about the research that y'all do, it would be such a struggle to get students to engage with that. So this is really wonderful.
I have to beat them off with a stick. I can't take everybody.
Yay, that's good.
I know.
Now, you both bring cutting-edge science into the classroom, which is such a strength. How do you incorporate your research into your teaching, whether it's general chemistry, physical chemistry, or your advanced lab courses? Does it get into the classroom?
Yeah, for me, part of the joy of being in a school like St. Mary's that doesn't just talk about teaching, also, emphasize faculties doing research and doing research with undergraduate students. So for me, teaching and research should not be two independent things, right? They should be complementary. So how do you blur the line between teaching and research? So when I'm teaching general chemistry, I'm thinking, what kind of how can I use my computational techniques to help these students visualize the molecules more, to see electron density, how that looks like. Then I teach a class in physical chemistry where we go back to the basics. We build up the Schrodinger equations, and how we try to solve these Schrodinger equations. Then I also have, as part of my course, an introduction to computational chemistry, which is actually, especially from the quantum mechanics aspect, which is an applicate, like just solving the Schrodinger equation, basically. So I try to help the student to see that these mathematics, they are not just abstract, right? We apply them and they become very useful, and they help us to see things, beyond what we could have actually thought of. And also to add, in my physical chemistry lab, right? This year I'm doing a cure lab, which is course-based undergraduate research experience. So it's one thing for the students to come to work with you as an individual, but now just by taking my class, I'm trying to help them to think like researchers, So for this semester, I'm giving them something very simple. They have two monomers, and these monomers are going to interact to form dimer. So they are using computational chemistry to understand what is really happening, how those dimers are formed, get the infrared spectrum and all of that. Then in experiment, they are also going to do an infrared analysis. So, they've met the lab technicians, they've ordered these systems that they're going to use. So they're going to do the interaction. So they're looking at it both experimentally and computationally. So I feel that would help them see themselves more as researchers and, just get them immersed in the full research experience. And once in a while, I tell them, like, for example, this cure lab, I say, if your results are good, I'm going to present it. I'll take it and present, somewhere. So please, do good result, because, I don't know what answers you're going to get. We're all trying to find out, something here. So yeah, it's been interesting.
And then they can put that on the resume that their results were presented.
Yeah, definitely.
By their mentor. That's wonderful. Emily, and thoughts about integrating research into the classroom?
So, like we mentioned before, the research extracurricularly is very well encouraged, but there is more cure incorporation, that course-based undergraduate research that Patrick talked about, where we are taking novel research projects. We don't know the outcome of them, and we are presenting it to our class, and we are doing the science together. And even if it's bad data, it's still data. Right? If we all want good data, not super realistic to get it on the first go. But in fact, I'm a little skeptical if you get it on the first go. But
it's going to be Google search, no research.
That's right. Literature search.
Yeah.
And so these cure-based programs in our classes are really interesting topically for us because we don't know the total outcome. And it gets the students excited because they're like, ooh, I'm participating, right? And I'm getting a grade for it. Lovely. For me, when I'm teaching my primarily upperclassmen, by that point, juniors and seniors, when they get to my biochemistry courses, they know they are going for med school mostly. med school, PA school. We get a few pharmacy students, and then a couple of graduate PhD master students. And so I cater my classes to the MCATs. They win the show. They are the majority. So I curate my classes towards them. And when we go to the lab component for, say, biochemistry, I try to relate these scientific topics that seem like they're not going to be useful for a future physician. I try to relate that back to, well, how is this going to help you day to day if you were an MD? And so something like taking an absorbance reading of a protein to determine its concentration could be translated for an MD as somebody who is confident interpreting results, making sure that you read your axes of whatever figure or graph you're looking at. Can you interpret these results? Are you taking the protein concentration of a patient's blood every day? No, but you are interpreting data and seeing, does this make sense? What are the pieces of the story coming together in treating this patient? And it's really, as far as research skills being implemented in the classroom, my focus is primarily on the critical thinking. Just because you see something, do you believe it? And does it make sense? Can you defend that it makes sense? Just because you did the math right and got the answer, can you back it up? And I know my students are tired of me because whenever, I encourage class participation and I say, hey, what's the answer to this? And they go, this. And I'm like, do you trust yourself? Do you believe that? Defend it. I agree with you, but defend it. Because once you're in a career where lives are at stake, you are caring for people, you have to be confident in yourself. And I find that some simple question of, can you back that up? Can you say it in a different way? Right? It challenges their brains in a different way, and it ultimately rebuilds their confidence. They know what they're talking about. It encourages learning in a new way, and it strengthens their understanding. And so trying to wrap all of that from research that seems like it doesn't relate to how can I apply these critical thinking skills largely in a day-to-day life for their future medical careers is one of my foci, plural.
This is really great. I would think I was speaking to colleagues who have been at the university with me for decades.
Oh, you.
Because you so wonderfully integrate scholarship and teaching, research and learning and service into the way that you even talk about your classes and the way you interact with students. It's really fantastic. Patrick, you've described your approach to teaching as being like a gardener, nurturing curiosity and letting ideas grow. How does that shape your work with students?
Yeah, actually, I adopted an analogy from Sack and Robinson, and it's
He doesn't
something
garden.
Yeah, I'm not a gardener in the real sense, but the concept of gardening, really describes what I am as a teacher. Unlike the industrial approach where you just build a system and you just get a bunch of products out of it. In fact, if a product is defective, you throw it away. You're concerned about the batch and you're thinking, how many can I get out? Because that's where the money is going to be.
Yeah, quota.
Right? But using an agricultural analogy, being a gardener, to start with, you only have a small space you're working with, right? So you're dealing with small number of students, and as a gardener, you need to have good knowledge of your plant species, you need to have good knowledge of the type of soil and what are the conditions, that would actually help your plant to grow. So as a gardener, you care so much about how each plant is going to thrive, right? And so to you, every plant has the potential to thrive, right? So the question is not if the plant is going to thrive, but what are those environmental conditions I need to put in place to help the plant to thrive. So that's the way I really see teaching. When my students come to me, I see them as individuals. I don't see them as a group. I used to teach at Baylor University. There I had, class size that varied from 20 to 100. And I also at certain point, I was a faculty in a university in Nigeria where I had class size of about 700, right? And to me, like the higher the number of students, the more difficult it is to know them on individual basis. And that really, kind of like weighs me down as a teacher, because I know I don't want to see them as on average, like a collective. I want to see them as individuals. So one of the first things that I do is I get to know my students individually. I know their names, I know their story. So if you come to my class and you're looking somehow, I'm that kind of professor that will ask, Emily, what's happening? Are you having a good day?
I'm in your class, doctor. I'm
Not
having a
your
great day.
Emily. No, just as an example. So yeah, so to me, the individual matters a lot, because at the end, we're not just teaching, we're also mentoring, right? So I've been in the teaching business since 2010. That's about 16 years.
Show off.
Even as young as I am, and I've had lots of students that still keep in touch with me, just because of the impact I was able to make in their lives, and to me, it's just, I'm giving back, because I am who I am today because of the impact that my professors had on me, so yeah, to me, teaching is not just about seeing your class as a classroom, but looking at those people that comprise the students in your class, what they bring to the table, what are the limitations they come with, and what are those pedagogical approach you can put together to help enhance their learning.
It's wonderful. Again, back to the interpersonal that we all try to do so well.
Yeah.
Emily, your ERACTA fellowship combined research and pedagogy, and you've known since grad school that you wanted to teach undergraduate. How has this training informed how you build your classroom community?
What Patrick brought up was that he's had personal experience being that one professor that impacted a student in such a way that it, even as small as made their day, but hopefully would have transformed them as a person. And I'm pretty sure you've got some of those stories in there. Some thank you cards that say my life has changed because I had you as a professor. And although I don't have 16 years in the teaching experience in business yet, I hope to have accumulated some of those stories. And I try to make the classroom not intimidating. And again, reducing that stigma that the hard sciences have. And again, bolstering confidence that students feel like they're not capable of. And making sure that they know that, no, you've got this. You actually know more than you think. And part of my pedagogical approach, my teaching philosophy, is that it's not just about the student's ability to receive information. It's also about how I communicate it. Because just because I present something in a way that makes sense to me definitely does not mean that every student is going to pick it up. And that's very silly to think that that's the case. I would love to be the universal communicator where everything I say is everything imperfect all the time. And that's just not the case. And so incorporating universal design learning into my classes to say the same thing in different formats, visually, audibly, with memes. I love memes.
Oh, I love
Oh,
memes.
yeah, I got to put
A
those
lot
in the
of it.
slides. Yeah, they really strike a chord with students and with me, because if I'm having fun teaching a class, then like what you mentioned earlier, Paul, the infection of having a good time, and it overall makes our jobs easier, funner, and students hopefully have a little bit of fun before their first or second exam. And so going back to, it's a two-way street with my teaching philosophy. Yes, I administer information, but I also rely on student feedback to make sure that what I'm saying makes sense, period. Did I write a question that is grammatically correct, for one, but also, is it misleading in a way that I didn't intend? And when I am looking at student results on exams and I start seeing the same answer over and over, and I'm like, there's something wrong that I did, or I proposed this question in a way that was misleading because these answers are not what I'm expecting. And so then I go back to the students and I ask for their input. Like, what did you think when you saw this question? And they tell me, and I'm like, okay, yep, that was not what I intended. And I ask, how would you recommend me reword this? And because most students are not trying to game the system to get an A. Most students are here because they want to learn and they want to progress themselves and hone their skills, right? And so when I ask them, how do I ask this question without giving away the answer? They've told me, like, I think maybe if you rephrase it this way, it might be good. And it's not like that answer, their suggestion revealed, like they followed the prompt. They rewrote the question in a way that wasn't too easy to pick up the next time. If you knew the answer, you would get it. And it's a way that I didn't think about presenting the question before. And so they're helping themselves in the classroom that semester, but we all know that it's really going to be helping future semesters when the next cohort takes exam 2 in Dr. Lancaster's Biochem 1, you know? And so it's like a parallel learning, reciprocal learning environment, I guess, maybe not parallel. And I definitely don't pretend like I know everything. And part of breaking the illusion of a professor sitting at the front of the classroom, for me anyway, is reminding the students that I am human, beep, bop, boop, and I make mistakes, and it's okay that I make mistakes, and I appreciate their grace for me, and I extend the same for them. They are of no exception. They're of no exception. They make a mistake. If it's a mistake on my end, I do my part to make it fair, right? I don't want to punish students for an error that I made, like, say, wording a question weirdly.
That's beautiful. That allowing the space for mistakes creates space for learning, and we can do that while still reaching for perfection in the sense that we do in education.
Ideally.
We ultimately want to get things right, but along the way it might get messy.
Super messy, but it's fun that way.
Okay, you've both spoken in different ways about making science more approachable and inclusive. How do you think about mentorship, especially for students who are still finding their voice or identity in STEM?
For me, just like I alluded previously, to me, I'm not just teaching, I'm also mentoring, right? So because I see my students as individual, I see myself as their potential mentor, that's able to help them beyond the classroom. Recently, one of my students, whom I taught as a freshman in 2011, back then in Nigeria, she graduated from Texas A&M, and she did so well that she had to give a commencement speech as a Ph.D. graduate. And she called me. I sat there, and she was making reference to the difference I made in her life, So to me, that's just like, seeing how much impact we can make. Because unlike when you go home, you sit in front of the TV, you don't know what's going to be shown to you, but you come to school with the intention of being transformed. So it's a very holy grail, holy ground for us, because these students are coming to us hoping we can help them find their voice, hoping we can help them get to the goal they want to get, right? And personally, I'm a first generation student. My dad didn't know anything about university application. He didn't know anything about the classes I want to take, what course, and all of that. I had to figure everything myself. So I can easily relate with someone that is underprivileged, coming from a minority distribution and all of that. It's easy for me to put myself in their shoe. I feel one of my superpowers is empathy, and once you can empathize, mentoring becomes very easy because you're able to put yourself in the student's shoes and try to see how you would navigate that situation. And another thing is, just like Dr. Lancaster said, right, we want to make ourselves very approachable I went to school and I couldn't approach my professors, but thank God for the ones that, made themselves approachable, So just giving them that environment where they can be themselves, where they know that they can just come to you and talk to you. My students call me Dr. O, like, hey, Dr. O, this is what I'm thinking about graduate school and all of that. Some of the students that took my class, physical chemistry, last year and year at St. Mary's, they still test me, oh, I'm doing research rotation, this PhD lab. What do you think? What do you think about this research, this lab, So to me, that's the power of mentoring. It's not just for the now, it's what you're building for the future.
That's so beautiful. For me, I mean, I feel like you set me up and I just, what can I say? But yeah, that, right? I think what I do want to add though, and I think you would agree with me, Patrick, about coming to undergrad study. These are typically very new adults finding their freedom for the first time. And the focus of getting your bachelor's degree, associate's degree, ultimately master's, Ph.D., is typically on academia, right? Getting the credit hours to graduate, getting the skills that you need for whatever future career you're trying to pursue. And I think the professors that made the biggest impact on me, they did want to push me academically. They wanted to make sure that I was studying and I was doing the right thing to get the good grades. But it was also the professors that just checked in on me and just wanted to know, hey, you doing okay? Like what you said earlier, like you come in looking a certain way and I'm like, that's not it. Are you okay? Right? Like there's something off. And I want to do that because I care. It's the empathy, right? But I feel like because there's so much of an emphasis at the undergraduate level to get the degree, that these young adults forget that they are developing personally. And so having somebody who's got a little bit more lived experience, just checking in and being like, yes, this is your degree plan, but how do you feel about it? Do you still like it? Are you doing okay? How's the home life? Checking in those ways reminds them that they are developing as scholars, but also as adults living in a society for the first time, typically on their own. And it provides that comfort that they're not alone. They're going through a huge transition too. It feels like it's not a huge transition because you get caught in this academic bubble. And it's like you're living on the dorm, or like you have a set schedule for, Dr. O's class in the morning and then Dr. Lancaster's class or lab later, and then you get caught up in this routine semester. And it's so easy to forget yourself because that focus is on getting the grades. And so the mentorship to me does the academic stuff, making sure that they're okay scholastically, but also making sure that they as a human are okay or going to be okay.
Yeah, I think there's this quote. Someone said it was said by Mother Teresa, but it says people don't care how much you know until they know how much you care. Right. So, yeah.
Let's step away from the lab for a moment. Emily, you're a gardener, a home improver, and a cat mom. What brings you joy outside the classroom right now?
Yeah, so unlike Dr. O, I am an actual gardener.
Shuts.
Oh, gotcha. No, so I mean, new faculty anywhere. This is my first tenure track position anywhere. Again, my dream job. Nailed it. When I say I nailed it. This is everything I want it to be. I put so much of myself into my teaching responsibilities and my lab responsibilities. Admittedly, there are very few hours in the day to recharge in a way. But because I enjoy it so much, I do find small recharge moments throughout the day, interacting with my students in a non-academic way, again, doing that mentorship role, getting an idea of, let's just step away from our academic bubble, talk human to human, person to person. And that I find that's very recharging and, bonding.
Yeah.
I think other activities that I really enjoy, I don't know. I enjoy it. My house seems to be on a ley line for cats. stray cats just find my house. And so one of my side projects is looking outside, making sure that there aren't any new friends outside. If there are, all right, well, we got to get them inside and find them a new house. And that seems to be the second most prevalent project that occurs in my life.
Nice.
Thank you.
Nice. Patrick, what do you enjoy when you're not teaching or coding molecules?
For me, I'm a person of faith. Like, I believe in God with all my heart, So for me, it's God, family, and soccer.
Yeah.
So,
Oh, yeah.
Not
when I'm
football?
not the real football.
Yes,
Soccer.
capital
The real
R, real
football.
football.
Yeah. So when I'm not coding, doing research and all of that, I want to spend time with my family. I have two precious little boys, sometimes when I'm away from the house. By the way, my son can tell you what I do in the class. Like,
Yes.
my dad is a quantum chemistry professor. I mean,
Yes.
what's quantum chemistry, So yeah, so I like spending time with my family. I like spending time at the church. I go to Bethel Church and I serve in different capacities. And then when I want to wind down, I like watching soccer, right? During my PhD, I actually played a lot of soccer, right? Whenever I'm just tired from doing research in the lab, we had this soccer, this group, we just come together and we play soccer together. But now I do a little bit of playing, but more of watching, and it's been fun. And another one I'm beginning to get more interest in. I went for the NBA games recently, and
The
the
Spurs
Spurs,
games?
yeah,
Nice.
they won. I was like, oh, I didn't
They
know.
won for you.
Yeah, I didn't know we have this much fun in San Antonio. So
Don't
that's
sound
going
so
to be my
surprised.
new fun stuff to do, right? Going to the games with my wife and all of that. So yeah.
Did your little ones get to go with you too?
Yeah, he did. He
Oh,
did.
I bet
It
he had
was-
such a good time.
Yeah, the game started, I think, around is it 8? Ended close to 10, 11. I was like, okay, we're sparing you
Right.
early bed just for today, right? But
Was he excited?
he was super excited.
You'll find no shortage of Spurs and soccer fans in the mathematics department. So
Hooray.
you guys are going to see us. Yeah. Taking a moment, if we can look forward to the horizon, what are some exciting things that you see for yourself personally or in your community or the like that you're looking forward to?
For me, in terms of research, is going to be collaboration. Just even from Dr. Lancaster talking, like I'm getting to see where we can collaborate for research. Just talking with colleagues and all of that. Just I'm beginning to see places where we can actually work together. So I'm looking forward to collaborating with my colleagues. Something else I'm looking forward to is actually, involving students in computational chemistry research, being able to arm them with those, just building a computational chemistry research system here at St. Mary's, hopefully. Right now I'm using like the common general computer lab. Hopefully I'm going to have my own personal computer lab where I can work with students. So just looking forward to that as well. And I'm also thinking about the possibility of helping students to get a certificate in computational chemistry, just giving them the experience and, involving them in some of these computational techniques and, just them getting certificate out of it, just something they can show on their resume. I'm looking forward to that as well. Then lastly, I'm looking forward to the dynamics that can happen in my class. At Baylor, I also did biophysical chemistry, so I didn't just teach general chemistry and all of that. So I'm looking forward to a future where I can begin to do some of those stuff I did before. I used to be the professor in charge of the biophysical chemistry lab. So now I'm doing just physical chemistry, but I'm looking forward to, including the biophysical component as well, where we do more enzymes, protein denaturing, and all of that.
Wow, that's exciting. Emily?
Well, many things. I'm always looking ahead. I have to plan ahead. If I don't plan ahead, then I lose myself, and then I have to rely on my phone calendar. If I live by it. If I don't, then it's lost. And some of the things on my phone calendar are, of course, my courses. Every semester, I'm looking forward to teaching a new group of students. And that sounds so cheesy, but it's so true. And you're so right. Like the changes in the course, Patrick was doing this with his hands, so now I have to do it. Yeah, every semester is a new thing, and that's fun. The university is creating a new garden space, and I'm on the committee for it. It's located behind the drone building in Moody Life Science, and it looks like dirt right now because it is dirt right now. But from dirt, cultivate, get plants, have fun. So I'm looking forward to that and making a sustainable garden that students and people from the community can visit. And then I'm also really looking forward to, you were talking about biophysical chemistry. When you're talking, I'm like, oh, that's going to be perfect for the new biomedical engineering program that's being developed by Dr. Elisa Isaacs. And she's doing it all by herself. Did you know that? No. She is a fierce woman. And when we bring these interdisciplinary programs, we really get this awesome opportunity to open up collaboration, which is just so exciting. And like, I'm greedy for data. I want to learn more about things. And even though I may not be good at physical chemistry or computational, I know that I have faculty here who can help me understand and help me, validate my excitement, because some results really are exciting or new research actually is happening. So largely that's what I'm really excited about.
That's super. So, Emily, we'll start with you. What advice would you give to a student who's curious about research but maybe unsure of where to start?
I think I said it earlier. Just find a professor that you feel comfortable with and open the conversation. And the thing about asking questions is you don't have to have the perfect question. Like, you can just start babbling, word vomit, and then eventually the question will form. And I think we sometimes get in our own heads about, well, I don't want to look stupid in front of my professor by not asking the right question. And I'm like, don't worry about that. Just get the question out. Like, we'll figure out what the question is as we talk. And if that question is, well, I want to do research. And then as I ask them more questions about what they're interested in, sometimes we find that my lab is not the one, right? Like, I don't offer what they're interested in. And so then I get them connected with the right faculty member or the right off-campus program to get them going with their research. And again, just encouraging them, letting them know that they are capable and can pursue this research if they want to.
Patrick?
Yeah, to me, I try to encourage the students not to be scared. Like, just come talk to your professor, because there are so many opportunities here at St. Mary's that you probably not get in a very, very big institution, So we as faculties were eager to get them involved in research, right? There's this thing that Steve Jobs said at his commencement speech at Stanford University, and I like that stuff a lot. He ended the speech by saying, "Stay hungry, stay foolish. Stay hungry, stay foolish." And that's really what I want to tell the students, right? Stay hungry, stay foolish, right? It's okay not to know anything about the research. We're not all about perfection. We're going to help you. Nobody knew everything from the start. We all, started from somewhere before we got to where we are, right? So they shouldn't be scared of sounding foolish, just like Emily just said, and also the hunger, the curiosity. That's something no one else can give to you, right? I can say things that will help you to have that hunger, but it has to come from you. And that is what is going to sustain you in research. Because we as professors, research, just like I said earlier, is not Google search where you just do something, you get the answer. Research sometimes can be boring. Sometimes you don't get the answer you want, So research needs commitment, right? So when you come to us, as professors, we're asking, is he or she going to stay for 1 year at least, right? Is he or she going to be committed, right, to the research? So all you need to do is be ready to be committed, then stay hungry, stay foolish, and we're going to help you feel the rest.
On behalf of SET Spotlight, thank you again to our guests, Dr. Patrick Oladamehin and Emily Lancaster. We invite everyone to join us again for the next episode as we continue highlighting the people advancing science, engineering, and technology at St. Mary's University. Until then, elevate your excellence, shape excellent tomorrows.
Thank you. It's been a pleasure.
Thank you.
Yeah.
Yeah.